Good afternoon, everybody. Thanks for joining us today. I'm Patrick Tucker, Technology Editor for Government Executive Media Group's Defense One. It's my great pleasure to welcome you to today's webcast, Changing Space Access Through Emerging Technologies, underwritten by SAIC. Today, we're speaking with representatives from the Department of Defense and civilian agencies to learn how they're harnessing advancements in science and technology to make modern space travel possible, space access, and creating an entirely new reality for the U.S. government activity in space. So whether it's new investments, satellite data collection, or using things like artificial intelligence or 3D printing in a new way, simulation, it's a very exciting time to be working on this new frontier. There's an entirely new U.S. military service branch that's been stood up, as well as a new combatant command. And every day I'm hearing more and more about how important space is to the future of virtually all government activity and certainly military activity, and also how the United States is no longer the only operator in space. It's becoming increasingly crowded, both in terms of geopolitical tensions and in many ways in terms of other objects that are up there. So it's really a wild, wild west. Today's program, we're going to be talking to four terrific panelists: Derek Tournier, Director of the Space Development Agency; Stacy Dixon, Deputy Director at the National Geospatial Intelligence Agency; Jeff Sheehan, Chief Engineer for the Space Technology Mission Directorate at NASA; and Colonel Russ Sheehan, Director and Portfolio Architect at the Space and Missile Systems Center for the U.S. Space Force. So thank you all for joining us today. Let's start with you, Derek, and then we'll just go around the panel. A quick 3 or 4 sentence introduction to who you are and what you do.
Certainly. Thank you for having me on the panel. So Derek Tournier, the Director of the Space Development Agency. The Space Development Agency is tasked with orchestrating the development, fielding, and operation of the next generation national defense space architecture. So we're putting up a completely new architecture based on proliferation and spiral development.
Great. Dr. Dixon, Stacy.
Awesome. Stacy Dixon, Deputy Director of NGA. Our job is to essentially show the way. So we are combining our knowledge of the Earth from seabed to space, and layering on top of that all of the information that you can glean from many overhead collections, so whether it's satellite or airborne, the knowledge of what's happening on the Earth. So adding those things together, providing geospatial intelligence to both Department of Defense as well as intelligence community partners.
Okay. Jeff.
Hey, good afternoon. Thanks for having me here. I'm the Chief Engineer of the Space Technology Mission Directorate at NASA, Dr. Jeff Sheehan, that's my name. Our job is to develop the new technologies that'll enable new capabilities and new missions as humans start to move into space and have a vision of working and living in space. We're laying the groundwork with our technology development for NASA's visions, as well as the visions and goals that industry has.
Okay. Colonel Russ Sheehan or Russ.
Yes. Hi, thanks for having me. So I'm at the Space and Missile Systems Center and also standing up the Space Systems Command. And we're one of several acquisition centers that are acquiring into the future architecture. And I'm spending most of my time making sure we're working with the force designers on where is the architecture going, making sure we're going after several of the flagship activities. And then I'm spending more and more of my time on making sure that we're creating a system of systems integrated plan across the multiple architectures so this stuff comes together on the battlefield. Thank you. Okay,
great. So you are part of the audience. We really want to invite all of you to make sure that you participate, especially if you have a question. This is a very rare opportunity to talk to leaders in a incredibly important and incredibly complex area of human activity. So if you have something that you want to ask about, especially as it relates to the government and space, emerging technologies, get your question in. We often find with these sorts of things that we don't have time at the end of the program to get to all the good questions that come in. So if it occurs to you, stick it in the queue. And if you have more than one, feel free to post those as well. We'll try to get to as many as we can. And with that, let me turn to you, Derek, and talk a little bit about what you're doing right now. You're buying a fleet of low Earth orbit satellites, and I understand from great Sandra Irwin article the other day, she keeps very good count of these sorts of things in Space News, that you've acquired 28 satellites with plans to launch 2022 for that transport layer, that data relay layer, where you're moving data across, really kind of low Earth orbit to much better facilitate communications between different objects in all the domains, land, sea, air, etc., requiring that transport layer for ubiquitous global communication. And there's 8 missile warning satellites you're looking to put up to track things like new hypersonic threats as they maneuver over the Arctic, towards the U.S. and hypersonics presenting an entirely new sort of threat. So a new space tracking there for those. And I understand you have plans for 50 additional satellites for launch in 2024. Can you tell us a little bit about what else you want from new satellites that are going to be part of future architectures? What else do you need?
Certainly. Thank you. Now, that's a good overview. It's closer to 150 satellites in 2024, though. That's our tranche one. So exactly right. So I'll talk through, the main architecture, and then I think that the challenges for what we need will become apparent. So the main reason we're putting this architecture up is to provide 2 main capabilities: beyond line of sight targeting for time-sensitive targets. So mobile missiles, ships, that kind of thing. We want to be able to detect them, track them, calculate a fire control solution, and send that directly down to a weapons platform. All do that from space so that we can close that kill chain in the order of seconds, right? So the second capability is to do that exact same mission, except instead of just time-sensitive targets, now we're looking at advanced missiles, hypersonic glide vehicles, dim upper stages, cruise missiles, etc. So in order to do that, you're exactly right. The backbone is that transport layer. The transport layer is the low latency data communication, all optically connected with laser comm. And then it allows us to communicate over existing tactical data links. So for example, link 16 directly down to a weapons platform. So we want to build that out and build out these layers. Transport is the backbone. Tracking is the OPIR for the missiles. Custody is ISR system, intelligence, surveillance, and reconnaissance, can be SIGINT, electro-optical, or SAR to be able to do that targeting mission. And we want to build that out and have it all be interconnected. So what are the problems and what do we need and what's the future? So the future obviously is proliferation, just more and more of these satellites. We're going to start launching in September of 22, and we're going to, every 2 years, we're going to launch new tranches of satellites to get hundreds and hundreds of these satellites up there. Now, the technical challenges, there's a myriad of them, and we've actually just put out a BAA to help us burn down some of our highest technical risks. Number one is the optical crosslinks. So optical crosslinks in space are not that new, but what is new is the ability to do them at a commoditized price point, the ability to do the optical crosslinks from space to space, as well as space to ground and space to air, and do that in a manner that it has a community of interest so that everyone can plug and play with a common standard. So we're looking at technologies to enable that. That's a big focus area. Second big focus area is a lot of what I've talked about is actually magical when you think about it. The ability to fuse all of these data, calculate a fire control solution in real time with multiple data sets, and send that directly to a weapons platform. That takes a lot of onboard processing. We call that our battle management, command, control, and communication. That is autonomy that needs to be built in. So there's aspects of algorithms and software as well as hardware that needs to be developed to make that work. And then another big area is how can we do all of this in a secure environment that we meet all of the NSA encryption models and requirements. And so to be able to do that in an affordable means to fit on these smaller type satellites, that's another technical challenge. So we're looking at developing those, we're looking at proliferating these systems, and we're looking at getting those capabilities out so that the warfighter can use them as early as 2022, and then have enough to where they could actually use it in a real fight starting in 2024.
Okay, and I also want to point out that the Sandra Irwin's article does say 150. I just didn't see the one in my notes here, but I want to stay with you for a second, Derek, because I have a question about you're talking about electronics miniaturization, computer miniaturization and squeezing more compute capability on satellites that you need to be increasingly small, because the smaller satellite, the smaller the cost of potential launching it, and the more you can get up there. Can you give us a size sense of the difference between these different satellites that you're thinking of? What does a transport layer data relay satellite look like in size, and how small do you think miniaturization may take it in the next few years? And how big is a missile warning tracking satellite as well? Because optical satellites, I know, are historically very large. There's only so much room you can expand glass, et cetera, in order to get a good picture. Are we thinking about it correctly? How small do you think these satellites, with the transport data relay satellites and the missile warning satellites, may be in the coming years?
Yeah, thank you for going down that path, because one of the key things, I'll give specifics on size in a minute, but one of the key things that I want people to think about when we're talking about these metrics. So in order to get this whole constellation and this architecture to work, right, we need proliferation, hundreds and hundreds of satellites, and we need to be able to get them up quickly. Every 2 years, we want to have these new capabilities. And realistically, the most important thing in my mind for that is the cost of the satellites, not necessarily the size. Size is extremely important in space, because obviously mass equates to the cost to get things up in orbit. But let's focus on the cost points. That's really what we drove to make sure that we can assure this compatibility with a proliferated architecture. So keep that in mind, and then I'll talk about how that folds into size. So in transport satellites, so we have transport satellites. 10 are being built by York Space Systems, and 10 are being built by Lockheed Martin. And each one of those is around 250 kilograms for the total spacecraft size. So that's the size of this transport bus, and that's notionally probably kind of the class of satellites we expect when we're up in the hundreds of class satellite. There's plenty of computation power for those types of satellites to be able to do this mission. There's plenty of size, weight, and power that we can put the optical crosslinks and do that mission. So that's big enough to enable you to do these kind of missions. Now, here's where we focus on cost over size, because they're not necessarily one-to-one with each other. On the tracking satellites, we again have two performers. L3Harris is building out four for us on those. And then SpaceX is building out another 4. And our tracking layer is actually made up of a heterogeneous system of medium field of view systems and wide field of view systems. So the 8 that I'm talking about from L3Harris and SpaceX, those are the wide field of view systems. And those will cue the medium field of view systems. And those are the 2 satellites that are being developed by MDA, who is a partner with us on this. And those 10 satellites total will make up our tracking layer. So now let's talk about size of the tracking satellites. So the L3Harris satellites are on that 250 kilogram class satellite, very comparable to the transport satellites. And you're right, if you want to do exquisite imagery, you need enough aperture to be able to get diffraction limited optics to be able to get high resolution. But when you're talking about tracking hypersonic glide missiles and things like that, you can deal with much larger pixel size on the ground, much larger ground sample distance, if you will. And so we're still talking about optics that are fairly small, easy enough to go onto a 250 kilogram class object. I mean, look at the imagery that comes out of companies like Planet, much smaller optics. And of course, obviously lower resolution. But if you're talking about missile warning and missile tracking type missions, that's sufficient. So the SpaceX tracking satellites, on the other hand, are much bigger. So those satellites are based off of a commoditized version of Starlink, where they have built from Starlink, and they've essentially increased the size to get a little more capability. But there you're close to 1,000 kilograms for one of their tracking satellites, doing the exact same mission. So there's no difference between what L3Harris is doing with their tracking satellite and what SpaceX is doing with their tracking satellite, as far as the ability to detect, track, and cue and calculate fire control solutions. All of those capabilities are the same. It's just one design is 250 kilograms and one design is 1,000 kilograms. Now, if you look at price points, so the prices are published on, these are firm fixed price bids. L3 Harris is coming in at around 194 million for their 4 satellites. That's firm fixed price, includes all their NRE, and then of course the recurring costs for that. SpaceX, on the other hand, they came in with their 4 satellites, came in right at around $150 million for those 4 satellites, including all the NRE and all of that, even though their satellites are 4 times larger. So we're focused on price because that's where you get proliferation. But of course, when you fold that into how much it costs to launch and things like that, obviously you have to keep in mind the mass of the satellite, because that starts to become a big deal, because you still pay, essentially you're still going to pay a certain amount per kilogram to get things to orbit. So that's the whole equation that we kind of use to look at this. Think about capabilities, think about how fast you can deliver something, and then look at the engineering on what the packaging looks like secondary.
Mm-hmm. Thanks. That's a very thorough answer. And in a little bit, I want to turn to Russ with more questions about that challenge of missile defense from space and how that's changing. As we talk about missiles, tracking them as they move along, the atmosphere of the Earth, but also tracking potential threats in space to space access. But first, let me turn to you, Stacy. And we just heard a lot about how SpaceX and different partners are really changing the game of private access to space. And Planet Labs is a great example. Rocket Labs is a great example from a different perspective, from like that launch perspective. And something that we've been watching over the last few years is, again, increased miniaturization of the satellites so that you can get more of them in space that are more capable, and not a collapse, but a downward trend in the cost of launching these things into space. So I wonder if you can say, from your perspective, what are the trends in commercial space that you at NGA are really looking to take advantage of in the next few years that are a little bit different from some of the ones that we've been hearing about in the past?
Thank you for that, Patrick. I'm actually just really excited after hearing Derek talk about what he's trying to do. That's like an awesome mission. With respect to the commercial satellites and what industry is bringing to bear, if you can just look at all the different phenomenologies that we've ever really had interest in, whether it's synthetic aperture radar, whether it is hyperspectral, multispectral, other better electro-optical at all different resolutions, and even bringing in things like RF, which is more on the sort of geolocatable data side, but provides a lot of really interesting insights for a GEOINT organization. We see constellations that are being planned and developed and launched that have all of these, both within US industry as well as international industry and international partners, governments. We're really excited about bringing that to bear to the GEOINT mission, because for us, it's not so much that you have to have, in the past, it was all about the classified satellites. It was all about the government-owned ones. Now that the capabilities are increasing so broadly in industry, it really is, how do you look at this whole thing as a constellation with which you can pick and choose what's going to answer the question for your mission partner, whatever their intelligence need is. And so as industry creates more of these different satellites, we're very excited. In addition to that, though, besides just trying to sell us or sell others the actual pictures themselves, we're really excited about the conversation they're having with us about services. So services in the sense of, what is the information that you can derive from the images that they're collecting through their satellites? Whether it is automated identification so that we can use that for tipping and queuing, whether it is some sort of service that just does some automatic metrics and measures for us and provides us some coordinates, or yes, no answer to whether something is or isn't there. There's a lot of companies out there now that are starting to use a lot more algorithm development with artificial intelligence and machine learning on their images. And we see a great market in being able to leverage that to also provide that to our mission partners. So figuring out how to manage it all as a constellation of both images and information is what we're trying to think about going forward in the future, and to get our mission partners to the point where it doesn't matter what the system is, as long as the system answers your question. But we have to start thinking about it as a larger constellation. And that is one of the things that we've been doing, is what we're calling our moonshot, which is, it's funny to have NASA online, but our moonshot is really much like what Derek was talking about. How do you get the information that your customers need to them more quickly, reliably, and safely and securely as quick as possible? And while we're paying attention, we're looking at missiles as well, but also from the perspective of where they're being shot from on land, where they're being shot from on sea, and how do we make sure that we can help hold at risk those things that would seek to do harm to either the U.S. or our allies. So we're just really excited about what commercial industry is presenting, and hope that they continue with the creativity and the just the variety of different types of sensors that they're thinking about putting on board on their constellations.
Okay, I want to. So you said something there, and I made me tremendously curious. Use of the radio frequency spectrum for geolocation. I've heard a little bit about using magnetic fields as a way to for objects to locate themselves in space. It's very experimental. It's very new and evolving. And I wonder if you could drill down a little bit more on that, on what you mean by that, and how important that is for NGA, because we'll talk about this in a second, but the GPS constellation, there's a big movement in the U.S. military to expand its options away from GPS just for the service that it uses. It's very widely used by everyone. It's increasingly a large concern in terms of national security, is the fragility of it. Talk a little bit about the use of radio frequency for geolocation and other tools that you can use to geolocate from space, and how those might even begin to change civilian life.
So first, let me clarify what I actually was saying, which is far less exciting than what you were just describing. Okay. I was really sort of making the point that even though radio frequency data isn't your traditional image, that because it has location information in it, that we as a GeoInt organization find it very valuable and are using that within the information that we're to leveraging that to help provide information and intelligence to our partners. To your other point, though, about the need to have other ways to geolocate beyond GPS, and certainly in those areas where GPS is denied, but in the future, just having other options. There's a number of different things that are experimentally being looked at to consider that. We also know that as we move further out into space and think about space more broadly, that we're going to need other frameworks than the one that we have established right now with GPS, that works mainly on up to certain levels above the Earth, but does not work in all of outer space that we might be interested in. So there's a lot of very smart people who are very well referenced or well educated in that sort of geomatics and geodesy area, that are looking at those equations and trying to come up with those different frameworks. So yes, that work is being done, but that was not exactly what I was talking about in that respect, that particular point. Got it. Okay, so yes, good to clarify, because that does bring up something that I want to stick with you with, and that is, commercial image providers now, there's a ton of them. I get great emails all the time saying, hey, we've got really awesome imagery of some geopolitical event that's happening right now. And NGA can certainly use that sort of thing to reach new insights. But, a huge part of being an intelligence agency is having an advantage, like an information advantage, potentially over competitors. And another trend that I've been talking to people about is a concern that, a satellite company that's emailing you photos or something from a particular standpoint, that's really great. But as soon as things start showing up on the internet, on the open web, then there might be a question as to the credibility of it. So I wonder if you could talk just very briefly about how, you just mentioned geolocation as a kind of way to enhance the credibility of any piece of information. So in an environment where there's so much information that's being put into the public view, some of it geospatial photos and things like that, how does NGA go about that process of making sure that it has information in a way that's a little bit more timely than everybody else, and that their accuracy is above just what's available on the open web? How do you address that challenge? Those are certainly investment areas that we are focused on, making sure that as we're developing government systems, that we are doing what industry isn't or can't do with respect to that level of precision. I'm actually very excited about the fact that there are so many different constellations out there. And I think that will be one thing that will help with that, what we're calling GeoInt assurance. How do you know that an image that you see actually is the thing that actually happened at the time that it happened? And by having multiple sources being able to all collect the same information, that's one way that you can pretty much, you can check yourself. Did satellite A and satellite B both see the same thing? And if they did at the same time, then you can believe it actually happened. If one of them saw it and another one didn't, one of those two is suspect. So I think that's actually going to help us with that realm, but making sure that all of the companies that we work with, or companies and governments that we work with, are investing in the cybersecurity that's needed to make sure that their data is protected. We're going to have to trust to some extent, but then we're also going to have to verify to make sure that we are be able to confidently provide the images to the customers that are counting on us to provide them that trusted data. So this is a growth area for us, especially as we bring in more sensors, not only just making sure that something like malware isn't embedded, but really how do you make sure that no one has manipulated the data itself? And we've seen a lot of that, those really great deep fakes where they manipulated both sound and images to make things look like they've happened. We have to make sure that we know how to catch all of those going forward in the event that adversaries or peers would try to do that to the images that we might want to use, that we're purchasing, that we don't completely control.
Yeah, absolutely. And this is something that we've covered at Defense One, using novel artificial intelligence methodologies like generative adversarial networks or GANs. You can create all sorts of imagery that may even fool algorithmic detectors of fake imagery. So it's a cat and mouse game that we're watching evolve very quickly. So let me turn to you, Jeff, because we've been talking a little bit about 3D printing. You've been talking about computer miniaturization, and we've been talking a little bit about artificial intelligence. As you survey all of the different emerging technologies that are increasingly available and are talked about in rather enthusiastic terms, perhaps by the pop science press, which of these emerging technologies like 3D printing or artificial intelligence or miniaturization do you think is going to change space access from a NASA point of view over the next few years? And where is there perhaps a little bit too much hype?
Well, we've had a substantial investment in additive manufacturing, or what people call 3D printing, for several years now in space tech. And we think the hype is real, actually. There are a lot of applications for that technology that we're working on. It'll enable us to make components and subsystems much more quickly and efficiently. We're developing techniques of recycling materials that have already served their purpose into new components, as well as printing with in situ materials, either pure elements that are extracted from places like the moon, or even with the soil itself. Initial implementations of that type of advanced space manufacturing have already been demonstrated on the International Space Station. And all of that, of course, requires advances in technologies to excavate, to extract, to process, and to store commodities on planetary bodies. The other thing is in-space manufacturing and in-space assembly, I think, is a big area for growth over the next decade or so. We've got a couple of demonstrations coming up, one that should fly in the next couple of years, one that's coming along a couple of years after that, to do substantial manufacturing of construction elements in space and assembly of final form, say, antennas out of individual elements. So it'll break that paradigm of you got to build something in roughly the final form, maybe with a few deployments once you get on orbit. You have to package that in a way that'll go in a launch vehicle fairing. It has to be able to survive the shaking and rattling of launch. So you really have to over-design stuff because of the loads that it experiences on launch that are much greater than what it'll experience in space. So if we can package individual components and assemble the systems that we need on orbit and manufacture elements of those systems on orbit from materials either that we take with us on the launch vehicle or we extract from somewhere like the moon, it kind of breaks that whole paradigm of we got to package this in a launch vehicle and it can't be any bigger than the launch fairing and we got to fold it up in some origami way and deploy it in space. We can just put it together from individual elements. So that's something we're working quite a bit on at NASA, and in lockstep with industry, we're working with Maxar on the demonstration of assembling a space antenna. We're working with a company called Made in Space, which is now a subsidiary of Redwire, on a demonstration to manufacture a 10-meter long boom in space that ultimately could be used as an element of a larger space structure.
And I want to turn to Russ to ask a little bit about space defense, but before we do, I want to stick with you, Jeff, and ask you a question that in covering Redwire and Made in Space and 3D printing in space, I've been very curious about, and I'm still hoping to get like an answer that makes sense to me. Can you describe the challenge of 3D printing in space versus like Earth? Like we understand how 3D printing works here on Earth. You can go to a place and they'll print you out a widget, and like the process is fairly straightforward. But in space, a lot of the same physical forces are completely different because it's space. You have different physical forces. That's why it's space. Can you talk a little bit about the challenge of trying to create something in space with a 3D printer when your frame of reference is always going to be 3D printing on Earth?
Right. The two big effects that change are gravity. You're always orbiting something in space, and so you have basically zero gravity or microgravity when you're moving at orbital velocities, and it's sort of like Buzz Lightyear said, it's falling with style, right? And so that's what orbiting is. And so you just never intersect the Earth; you just keep falling. And so it's the gravity effect. We're so used to manufacturing things in a 1G environment on Earth that all the processes have to be adjusted for that. And then the other is the thermal control. We have this atmosphere on Earth that we can dump thermal energy into, and we can construct big apparatuses on the ground to control the thermal environment. But so thermal control in space is another significant factor that changes. And so the processes that you develop on Earth have to be modified, in some cases reinvented, really, to make them applicable to the space environment. Even things like welding that you do, sort of, it's a very well developed technology on Earth, been going on for hundreds or maybe thousands of years in some forms, and that has to be reconfigured and re-engineered to apply to the space environment. So those are some of the technical challenges that you encounter in trying to move something that's a well-developed process on Earth into the space environment. And the other speakers on the panel have a lot of experience with that in their realms also. It's really when you try to package something for the space environment where the engineering rubber kind of hits the road, and you have to look at all sorts of challenges that you don't really have to worry about when you're in the Earth environment.
Mm-hmm. It's a huge challenge. So let me turn to you, Colonel Sheehan or Russ, and tell us a little bit about. You were the portfolio architect at the Space and Missile Systems Center for the U.S. Space Force, and the Space Force and the government in general has been a lot more open in the last couple years or so with the types of threats that the U.S. faces actually in space from adversaries like Russia and potentially like China. But Russia in particular has been doing some really interesting and threatening things with objects in orbit that the Space Force has said potentially threaten U.S. space activity. Can you talk to us a little bit about how you think about the future of threats in space to what you're doing in terms of portfolio architecture and how that's beginning to enter into what you do in terms of, an activity that you didn't used to have to think about threats in space to putting up a missile tracking satellite and how that's beginning to change.
Yes, again, thanks for having me. I should probably start with, and Derek knows, I'm an offensive space control person from the past. So I know exactly how I would go after our architectures. I've known for 20 years how I would go after our architectures. So as the portfolio architect, I focus a lot on where are we vulnerable? Where do we really not want to take a hit? If we lose an asset, and it was 1939 and we're entering into World War II and we lose an asset, and it's 1946 or 47 before something else comes on orbit, That's not good. So most of our strategy back at the center, and we're working with Derek, MDA, and multiple others, is looking to get into higher rate production, simpler platforms, distributed. But in many cases, that gets to tough discussions with the requirements owners on getting to that min viable product. What do we really have? And we as a nation are so used to building engineering marvels, right, that are just the best systems, the Hubble telescope equivalent system. That's great, but it puts us into a single system. And remember, Hubble had its measurements wrong, and then we had to build a whole other mission to go update from the, to the metric system. The same stuff happens within the space architecture, where I focus at the enterprise level on where are we putting too many people, too much money, too much energy into sub 10 element architectures, and how do we rotate to the future where, frankly, like the Incredibles, no one is special. I am not worried about losing anything because it's really hard to guarantee that anything in the architecture will survive. If someone really wants to go after you when you're off the planet, it's really hard to guarantee that you're gonna make it. So the things we're focusing on are maneuver, distributed architectures, layered architectures. We're doing, and that's again what I said earlier, that's where everything we're doing with MDA, SDA, multiple other centers that I don't want to get into, but there's multiple other groups that are acquiring. And right now we're trying to acquire at higher rate production. Every portfolio, like within PNT, GPS is still the quarterback. We are still expecting GPS to be the quarterback. But I think Stacy brought up earlier, there's a lot of things we're doing where I can distribute those signals within Derek's architecture, or things we're working with Stacy and NGA and other areas. So every area is heading to an area where you have a quarterback, but you do everything you can to do appetite suppression of adding too many requirements to the quarterback, which burns the national treasury and the quarterback, and there's no wide receivers out in the other layers that could be distributing the architecture. So everything we're doing is trying to distribute. And I would say in the deep space architecture, simplifying the architecture, going to maneuverable, that is creating a lot of calm, like the need for cross links, data movement. And it's definitely creating layered architectures with Derek, Rich Ritter at NDA and others, where we are now having to move data vertically across multiple layers and get to really timely solutions, and simultaneously move data to theater in a geographic COCOM like Indo-PACOM or UCOM, but also move it back to the US. So that's another major change within the architecture. We're used to dominating and sending data home, analyzing it, and sending out products within OPIR and other areas, and we are not going to have that luxury in the future. So that's just a few of the things that we're working on.
Yeah, no, that's a ton. And the idea of satellites that maneuver to dodge incoming, I mean, this is a crazy science fictional thing, but it's something that now we have to think about and talk about. So we've got a question from the audience, and we've got a little bit of time left. So if you've got one that's burning, I want you to try and get it in if you can. This one comes from Patty Nyberg with AP in Denver. And she asks, what are your thoughts on the Trump administration's decision to move the Space Force headquarters from Colorado Springs to Alabama? Do you think this is the best in terms of what each facility has technology-wise, expertise-wise, et cetera? So a bit of background there. It was a couple of weeks ago, an announcement that Space Command headquarters was going to have a permanent base in Alabama. It's currently headquartered in Colorado Springs, along with NORAD, along with Peterson and Schriever Air Force Base. Alabama has the Missile Defense Agency, so there's that. A lot of questions about whether or not there was political motivation there. Anybody want to weigh in on the benefits, drawbacks, thoughts, etc., on moving permanent basing for Space Command headquarters to Alabama from Colorado Springs?
Yeah, honestly, I don't really have any big thoughts in that area, and that's I stay out of all the basing and what have you. Hopefully it'll bring a rise of Army and Navy presentation, moving something back east. But again, I have no idea what went into the basing and what have you. But there's I'm hoping that will, at a minimum, as you said earlier, increase the presence of the Army, which again, the Army's doing tons of great stuff with us in PNT, SATCOM, and so is the Navy. So who knows? You can only hope that that it'll create the force of the future. But I really don't know what else went into it. Over.
Okay. Yeah, understood. It's a tricky decision, and no one who made it is here on this call, so I'm not sure how to help you with that. So let me turn really quickly, in the time that we have left, to each of you to a quick statement on some aspect of emerging technology, like artificial intelligence in particular. Let's focus on that. How you think that's going to change what you do in the next 5 to 10 years. And because not a lot of people know this, but Dr. Dixon was the head of IARPA for a long time, which makes her kind of a polylingual expert in information technology as well as space technology. Your thoughts on how artificial intelligence is going to change NGA in the next few years? And then we'll go around the table to everybody in terms of how AI changes what you do.
So one of the things that AI will allow us to do is to put, I would say, machine eyes on every image, every bit of data that's coming through. There's so much coming now because of all the different constellations, both within the government-owned ones, the classified ones, to all the way to all the ones that our industry partners and international partners are providing. There just aren't enough people to look at it. And to the point made earlier, you want to be able to make decisions very quickly and get or develop information intelligence descriptions very quickly and be able to get that very quickly to the people who need it for whatever purpose, whether for targeting or whether just for information and awareness. Allowing us to do things at machine speed is going to move us in that direction. Now, we need to also make sure that the architectures that we're developing have a great combination of ability to develop, ability to be very secure and to operate. So to have that DevSecOps environment where you can constantly be iterating on your algorithms, that's the only way that we're going to actually achieve the benefits, I think, of what AI and machine learning can develop, is being able to do a lot of things very quickly on the fly and then reiterate and doing spirals on those things. So there's a lot of promise, but if we lock in and make it too rigid, we won't actually ever achieve that promise.
Excellent. Derek.
Yes, thanks. So as I mentioned before, the key thing that we're looking at is closing that kill chain in the order of seconds. And so the first thing that you could think of is, wouldn't it be great if I had some AI and machine learning and almost supercomputing power availability on orbit in order to do that? And as Dr. Sheehan mentioned earlier, I'll summarize what he said when he was talking about the differences in 3D printing on the ground and in space. Space is hard, right? And because of that, let's think about the actual engineering challenges to AI in space. So while we're getting better and better at computation and the actual electronics are getting smaller and more powerful, in the end, you're still going to be limited by how much power you can dump, how much heat you can dump for these processing capabilities. Whereas on the ground, I can tie myself to a hydroelectric dam and a river to cool my processing center, right? I can do as much processing as possible. But in space, you're always going to be limited by the amount of heat you can dump and the amount of power you can collect. So the way I view it is, keep in mind, I'm viewing from a myopic vision, because what I want to do is I want to get capabilities up as soon as possible. So I'm looking at what is the state of the art that I can fly in 2 years, 4 years, 6 years, and I'm thinking in these 2-year chunks. So the way I look at it is, in 2 years, I'm going to go with essentially what DARPA has developed for the Pit Boss program as part of Blackjack for the onboard processing. But in the future, so in 4 years, what I want to be able to do is I want to be able to take AI and machine learning algorithms that have really been masterfully designed by mostly from folks like Stacy's organization at NGA, where they've really figured out how to do that data fusion and how to come up with those algorithms and then port those algorithms to run on space. So we're not going to be doing the AI and machine learning in space. What we will be doing is applying machine learned algorithms in space to be able to do that automatic target recognition. That's kind of 4 and 6 year time frame. And when you get further out, that's when you can start to really network and have cloud computing in space through these optical comm links. At that point, then you can start to get some computing power to start to do some of the new machine learning algorithm development on board in real time. But it's really going to be done on the ground first and then ported to space where you're power and thermal constrained.
Excellent. And once you have cloud computing in space, then you can have Bitcoin mining in space, and then buy or late. No,
that's
kidding.
Right. That's right.
Kidding. Don't I'm not advocating actually buying Bitcoin, but Bitcoin mining in space is a real thing. Jeff, to you.
Yeah, certainly the NASA Science Enterprise has some of the same interests that Dr. Dixon talked about in terms of image processing and applications of artificial intelligence to that. At Space Technology Mission Directorate, we're developing high performance processing capabilities, be 100 times better than the rad hard processors that we use in space now. That's a project we have underway. We've also been looking at neuromorphic processing, which is neurobiological influenced processors that build in artificial intelligence capability. A lot of the applications that we see for our missions over the next decade or two are in autonomous systems that tend and monitor large assets that have been placed. Sustained presence off the surface of the Earth is going to require a lot of assets to be in place that may not have humans tending them for long periods of time. The humans will be there intermittently, and so they'll be there for years. They have to be maintained, they have to be tended. And if you think about the movie The Martian from a few years ago, what you didn't see in that movie was a lot of Star Wars like robots walking around. What you did see in that movie were intelligent systems monitoring the vehicles that were placed on Mars before the astronauts got there, and the vehicle that was taking the astronauts to Mars. So those kind of implementations and that type of autonomous system and intelligent system monitoring are applications that we're actually actively working on and that we see for our missions.
Wonderful. Really quick, Russ.
Yeah, I think we're into a lot of the same stuff that everyone else talked about. Our focus in our main mission area that's flagshipping a lot of this is the deep space domain awareness. That's where we really just don't have time to phone home, process everything, and then send back a point solution, right? So we're looking to everything Derek was saying down low. We're also looking to do up high with deep space, highly maneuverable space domain awareness assets that are looking to collect that information, have a comm architecture up high that's moving that data around and making decisions and cross queuing to get you the information fast. Over.
Okay. That was great. And we're out of time. I want to tell you all to stick around for a second. We're going to get an industry perspective on changing space access through emerging tech from Daniela Fayer, publisher of Defense One, talking to Jim Light, Senior Director of Space and Strategy for the National Security Group at SAIC. But in the meantime, I want to thank my panelists for joining me today. Love you guys. Really appreciate that. And Daniela, over to you.
A big thanks to our editorial panel. Hello, everyone. I'm Daniela Fayer, publisher at Defense One, a division of Government Executive Media Group. And it's my great pleasure to continue the conversation this afternoon with Jim Light, Senior Director of Space Strategic Development at SAIC. Hi, Jim. Welcome.
Hi, thanks for having me. Pleased to be here today.
Well, Jim and I have met before, but for the benefit of our audience, I'm going to ask you if you could just spend a little bit of time giving us your background and how you arrived at your current role at SAIC.
Sure. As a kid, I watched Neil Armstrong land on the moon, and that inspired me to get into the space industry. So After completing college, went into the Air Force and served in a variety of positions and worked with NASA on space shuttle. I worked in the intelligence community, and I worked with DoD space programs. So that was an exciting time, but industry was beckoning, so I jumped over to industry after about 13 years. And I've been in a variety of companies since then. For the last 6 years, I've been at SAIC, working space strategy, and it's been a fun ride. I've been in space now. This is my 40th year in the space industry, and seems like there's never a dull moment.
Well, that's exactly why I was enthusiastic about our conversation today, because given your perspective, I think our audience would really appreciate understanding what you think are the space priorities of the future.
Sure. There's never been a more exciting time to be involved in the space domain. I've never seen this amount of change occurring over such a short period of time. And I see that being driven by 5 primary drivers that are impacting the space systems and the space enterprises that we're starting to produce and roll out now. The first driver is that heavy commercial investment in LEO constellations, in launch, and now even in human spaceflight that we've seen with the successful Spacex NASA launch, which was very exciting. And that investment includes everything from broadband comm to disadvantaged users to a growing amount of commercial remote sensing systems. We're selling space data as a service. The second driver I see is the hypersonic threat. That forces us to change how we do our protection against incoming missile threats. So we need low latency command and control, all the way from threat detection to system engagement, and then finally to defeating the threat. The third driver is the continued growth of contested and congested space. The growing number of satellites there has increased the need for collision avoidance and space traffic management so that we don't accidentally collide between satellites and create cascading failure from space debris in one of the orbits. But on top of that, the congested aspect of space, or the contested aspect of space, I should say, drives the need for resilient architectures so that we can avoid and withstand losses in our systems, and we can evolve those systems faster than the speed of the threat. The fourth driver is humans getting back to the moon and then on to Mars. And how exciting is that? I'd love to see, the next human land on the moon, but more importantly, love to see the first person walking on Mars. How exciting would that be? And then the fifth is one that I see just coming up now with the change in administrations. I believe that Earth observing satellites and observing the environment from space is going to have a renewed emphasis that was downplayed in the recent past. So when you combine all these demands that are changing what we need to deliver on orbit, what that drives the need for is a widely interconnected digital ecosystem and the application of cloud, artificial intelligence, and machine learning technologies to that ecosystem.
So Jim, you closed with mentioning this digital ecosystem, and I want to dig in there a little bit. Can you explain to our audience and to me a little bit more about that concept? What are the enabling technologies that are part of this new digital ecosystem?
Yeah, so the future of space is a digital enterprise. It's changing the way we buy and fly spacecraft. We have to integrate data from disparate systems, and those aren't just space systems. It's from space and non-space domains. And we have a growing number of players that can provide data that would be useful to our end users. So we have to take that data and then apply it rapidly to either decision-making or to getting, fusing and disseminating information to the end users who need it. Through both our C2 systems and our comm systems. And that has to be done with low latency, as I discussed before, to any place on Earth. So it's an interesting challenge that just continues to expand. If we look broader into that evolving ecosystem, this is not just something that's going on in the defense industry. It's going on with our civil partners and with the commercial providers. And everybody is trying to take advantage of the digital ecosystem to do things better, faster, and cheaper. As a result of this digital ecosystem, the other evolution I see happening in parallel is the fact that the satellite is no longer kind of the focus of an acquisition or focus. It's not the end game in and of itself. Instead, it's becoming, how do you integrate what's on the satellite into that digital ecosystem? So satellites are evolving from being the focus of what we put on space I shouldn't say just, but to becoming more of a sensor or a data provider on orbit, and another node on a network that goes beyond the space domain. That, of course, changes buying habits. We're not buying standalone stovepipe systems anymore. We have to deliver systems that come out of the box, plug and play, so that we can take advantage of data fusion and link systems together so that we're more resilient to survive the threats out there. Digital engineering, agile processes, what I like to call agile everything, and cloud technologies are all foundational to achieving that digital enterprise that I just described.
So this is a growing and diverse ecosystem. So the question I have beyond that is, how do the space operators acquire systems to enable their missions? As they're doing this, how does the ecosystem, drive the cycle around that for them? Could you, just dig into that a little bit for me?
Yeah, sure. Space operators have a different focus than they did when I grew up in the space industry. You can't just focus on one satellite that you're flying. You've got to focus on how you fly the enterprise to deliver capabilities to the end users, whether that be someone trying to protect our space assets or on orbit, or someone out in the field who needs that data on the ground. So we're migrating from a stovepipe system type management approach to, we've been evolving to system of systems, but now we're even evolving into integration of whole enterprises together. So the challenge is, how do we do that in this complex environment where these enterprises are evolving on a much more rapid pace? Certainly digital engineering is an accelerator for doing these complex integrated enterprises. We're already starting to see systems that are designed from scratch with digital engineering. And what that enables is that we're able to do early integration and test before we even start bending metal. So it's an accelerator in how we produce new capabilities to put on orbit. And then underlying that, the open architecture is absolutely critical. You have to have something to plug these plug and play satellites into. These are not the monolithic stovepipe C2 and data exploitation systems of the past, where we can put it out for procurement to a single vendor and wait 10 years for them to produce it. We need this open architecture facilitated by the cloud technologies and connectivity, so that we can more easily scale and on-ramp new technologies and capabilities. We can't wait 10 years to put out new systems. So open architecture is absolutely critical to being able to on-ramp new capabilities and adjust how we fly those systems more rapidly. That open architecture, again, drives us to distributed or perhaps hybrid cloud solutions that are connected by ubiquitous, high-speed connectivity and transport. Underlying all that, the AI and ML that I talked about before, and the digital engineering I talked about before, are foundational enablers to take advantage of this integration of enterprises. It's about leveraging the latest in those technologies to the entire life cycle of space assets, from where we're thinking about what we want to do next with our systems, to how we acquire them, to integrating them into the enterprise, and then eventually how the operators fly them as an enterprise, not as a single system. And then we can't use our old slow systems engineering processes and software development processes. So agile software development, agile systems engineering is needed from everybody who's contributing to this enterprise, so that we can take advantage of rapid development and capability and refocusing capabilities as threats change. So, we're going from what used to take decades to produce monolithic software to years for plug and play kind of apps to where, if we do agile DevSecOps, we can produce new capabilities daily as the need arrives. So in closing, I mean, what an exciting time to be in the space industry. If we apply digital engineering to this cloud-based open architecture environment, those are foundational to enabling the agility that is required both to meet the ever-emerging threats to our space enterprise, as well as to deliver critical capabilities and data to end users, whether they be commercial, civil, or military, and wherever they may be, either somewhere across the earth or deep in space. So I can't think of a more exciting time to be in the industry, and I'm proud to be part of this evolution to this digital construct for our space enterprise.
Jim, thanks so much. That's unfortunately all the time we have today, but I'm so glad you stuck with it for all these years, because it just seems to be getting more exciting. I want to thank you for joining me today, and I want to thank SAIC for making today's event possible. Many thanks also to our audience for tuning in. This was the third and final installment of our State of Space series. You can watch the first 2 episodes on demand at defense1.com. They covered digital transformation in the defense and space domain and new orbit, space, and all-domain future. Check them out and enjoy. Thank you so much. For Defense One, I'm Daniela Fayer.